In this episode, we're going to consider some tips and tricks for building neural networks that will prevent overfitting even rather complicated architectures. So we start with first step of training a neural network, initial weight suggestion. So let's consider an example of a neural network. And what if we make weights for such a neural net equal to the same number, say to 0? How would the gradient descent work? So obviously, when we run the gradient descent, then within each layer, the gradient for each of the weights will be the same as well. So it means that all the updates within the gradient optimization will be the same, and the network effectively reduces to a much smaller one. So, okay, so we know that weights should be random. How random should it be? Let's go further and see what does the size of the matrices of the weights affect. So if it is too large, is it good or bad? If it's too small, what could be the problem here? So let's take a very simplistic approach. Let's forget about nonlinear layers, and we just consider a neural network consists of matrices multiplied one by another and by input vector. So, or it could be a case when the nonlinear unit is a rectified linear unit that, as you remember, looks the following way. So it is 0 up to 0 and then equals to x in the positive part of the x space. So now what would be the gradient of such a function with respect to, say, any weight in the middle? So if we compute the gradient of the loss function d something in the middle, according to the chain rule, it would, well, you don't need chain rule here because it's just a math. It would be multiplication of all weight matrices except for the one that we want to compute, multiplied by x. Well, it's a little bit more complicated because of the matrix multiplication linear algebra. We have to transpose and to keep the correct order. But the idea here is that gradient that we want to compute is proportional to multiplication of all weights of the matrices. It means that if this product is too large, the gradient values will be too high, and we will not converge to the minimum. We will just keep jumping up and down, and it will not result in a convergent trajectory. Or if this product will be too small, the steps that our gradient descent is going to make will be too small, and this is the opposite problem. It is called vanishing gradients. So this basically shows what I have drawn before. So the gradient is proportional to some characteristic scale of the weight matrices, or some, if we consider what matrices 1 by 1, so the gradient will be proportional to the mean value multiplied m minus 1 times, where m is the depth of the network. And yes, as I said, if this characteristic mean value is too large, the gradients will explode. Otherwise, if it's too small, the gradients will vanish, and in both cases, the optimization procedure will not converge successfully. A little more detailed description of the process. I'm not going to focus on this in greater details. Just want to outline that the idea of the stable learning network should keep this equation true, like variance of two consecutive layers of the gradient of two consecutive layers should be more or less equals to the variance of a given layer. So it means that the gradient doesn't change much as we transverse through the layers and compute the gradient in our backward rule. And if we are talking about the forward pass, then scale is also becomes important because we would like to keep it more or less regularized, and it means that the variance of the output of two layers should be equal to the output of a single layer, variance of the single layer. And random initialization would be good if we manage to keep those two equations true. And in general, those two requirements may contradict each other. For example, for ReLU activation, the result in initialization requirements that is inversely proportional to number of outgoing connections and not inversely proportional to number of incoming connections. And it's difficult to satisfy those two requirements. So typically, people just choose one of them or average them out. So let's take a look how the overfitting of neural network can be easily can be. So let's look how overfitting of neural network can be addressed on the layer level. As neural networks contains of many coefficients, it's quite natural to see the case when our training sample is ideally or more or less ideally learned, and the loss function shrinks to very, very small numbers on the training sample, while validation sample loss function becomes quite significant. And this is a scenario that is usually considered as overfitting, and in reality you see that if given two data set of yellow and blue dots, the decision boundary tries to pick a very tiny pieces of objects that clearly belong to the opposite class. And when you test such a neural network on a training or testing sample that hasn't been exhibited during the training process, of course, there will be yellow points falling into such peculiar details of the decision boundary, and it will result in some penalties and high values of loss function. As you remember from the logistic regression discussion or linear regression discussion, one of the common techniques that address overfitting problem is regularization. And common cases of regularization employing L1, L2 norms that prevent high number of weights to be reached during the optimization process. And another another method for preventing overfitting calls early stopping. So it means that we demand that the training stops as soon as validation error starts to increase. So like in this region, we start to see that the validation error becomes higher and higher, and without subsequent decrease, and it is a clear sign that we have to stop here, because it means that we are starting to see such unwanted artifacts in our network performance. Regression and linear models, we can remember that one of the meaningful methods to deal with overfitting is called regularization, which means that we add to the loss function not only accuracy of the model performance, but accuracy of model classification, but also, for example, some of the weights or squared weights sum, which prevents the model growing those weights too large, and thus going into some overfitting direction. In case of neural networks, this method can also work. However, we can take advantage that the structure of neural network is essentially captures the features, and overfitting patterns can be somehow spotted amongst the neurons. And if we try to remove some of those connections during the training, we will prevent appearance of some unwanted configurations that affect the performance, like we saw in the previous slide. And this method is called dropout. Essentially, it depends on a single parameter, which is a probability of turning activation of certain neuron into zero. Basically, it is a layer that is applied to the neurons of the next layer, essentially performing this zerification. And during test time, it multiplies the activation by p, and sets it basically to the expected value. And what it effectively does is it makes neurons learn to work with a randomly chosen sample of other neurons. So this neuron can, during the training, it looks at the patterns of signals coming from the previous layers from those three, and on the next epoch it will learn to get images or signals from other combination of input neurons, which means that it will rely on some pattern that sustainably and robustly exist in the data. And the second effect is that dropout drives towards creating useful features rather than relying on other neurons to correct it. Examples that imply using a dropout procedure and some regularization technique. So here we have in this figure regular training, and if we add dropout, we get something like this. Or for two-dimensional classification problem. Without dropout, you see clear overfitting patterns, and with dropout, there is no such peculiar there are no such peculiar zones. So as we saw, during optimization, it is really good to keep the variance within certain boundaries. And there is an effect that is called internal covariance shift that updates in one layer change the input distribution in the subsequent layers. And if the output of our layer becomes a little bit different, and the output of the subsequent layers shifts also, and it may happen quite unexpectedly. To mitigate this, the technique of batch normalization has been introduced. It works in the following way. So we calculate sample mean and sample variance on a single batch. So it is mu b and sigma b squared. And then we normalize the input and then the scale and shift it with the trainable parameters gamma and beta in the following way. And this is it. So we just normalize the batch values in the training sample. So it turned out to be quite powerful technique, and besides making results more accurate to compute, it also converges much faster. And later was proven to not reduce the internal covariance shift. And effectively, it removes the shift and scale degrees of freedom from the previous layer. So when we're talking about batch normalization, you may ask yourself which dimension you should normalize over. In case we have a data set, in case we have a data set of features or one-dimensional vector of features, we effectively have a two-dimensional tensor, number of elements times number of features, like a table you can imagine. And thus you can separately normalize in the batch along every feature, F1, F2. So, and this is a batch size. And you can normalize either individual components, or you can normalize like the whole vector. Things may be a little more complicated if you have multidimensional object, because you can, in addition, splitting by those special dimensions, width and height, for example, you can also separately compute these statistics for individual channels. And here is the illustration. Don't worry if you don't understand this, because we're going to describe how to construct a neural net dealing with images on the next lecture next week. Normalization at inference time implies calculating batch statistics, so mean and variance at training. So because at test time it's maybe difficult, because there will be not enough object to estimate these values. So we compute it during the training and apply those at testing time. And here is a quick example comparison of the cross entropy loss function for convolutional neural nets on MNIST dataset. And you see when you add dropout, you improve the quality significantly. So it brings us to the summary of this episode. We should be careful when doing some tricks with neural network. In particular, initialization can lead to wrong consequences, but also correct initialization may be highly beneficial for the neural network performance. To deal with overfitting, there are standard techniques for regularizing it with L1 or L2 penalties or with early stopping, and additional neural net allowed to introduce dropout that let neural network forget some overfitting examples. And also in evolutional sense, dropout makes neurons create useful features rather than rely on other neurons to correct their mistake. And batch normalization is an extremely powerful technique that really helps to improve accuracy of neural networks. And okay, so a good question to you: how would you implement an early stopping rule? And I hope during the seminar this topic will be also covered. Thank you very much for your attention.